Hi, I'm Patrick from Validity, and today we're going to talk about 3 dial indicator concepts: total indicator reading, or TIR, the validity rule, and true position sensing. I'll zero my dial indicator at 12, and then roll it 180 degrees to 6 o'clock. It reads 30 mils, which represents the total indicator reading, or TIR. Now, as you're probably aware, the actual vertical offset of the shafts is half the TIR, or 15 mils. This is because when using a dial indicator to measure the relative positions of 2 shafts, the dial reads the misalignment on both sides of the center line, so the value comes up as twice the actual offset. The same is true if I zero the dial indicator at 3 o'clock and then roll 180 degrees to 9 o'clock. It reads 20 mils, the TIR, but the actual horizontal offset is half of 20, or 10. Next, to introduce the validity rule, let's set the indicator to 0 at 12 o'clock. Now we're going to take readings every 90 degrees for the full 360 degrees. We call this taking sweep indicator readings. So first, let's get a reading at 3 o'clock. There, we have 5 mils. Now another 90 degrees down to 6 o'clock. And that value is 30 mils. Next, we read at 9 o'clock, and that reads 25 mils. And then back to 12 o'clock, and the indicator comes back to 0. The validity rule states that when we rotate the shafts, the value we acquire at the top plus the value at the bottom must equal the sum of the value at 3 o'clock and the value at 9 o'clock. So we had 0 at 12 o'clock and 30 at 6 o'clock. We had 5 at 3 o'clock and 25 at 9 o'clock. So top plus bottom must equal side plus side. The power of the validity rule is that we don't have to rotate a full 360 degrees in order to get accurate alignment information. That can come in very handy if we have obstructions. For example, with a lot of small machines, it's impossible to get a reading at 6 o'clock. We only have to rotate 180 degrees and take just 3 readings, since if we know 3 of the values, we can always calculate the 4th value. Whether you're using dial indicators or a laser alignment system, this rule still applies. The validity rule is also the basis of a powerful measurement concept that Validity has pioneered, which we call true position sensing. I already have the indicators at 12 o'clock. They've been zeroed, so I'm going to roll it down to 6 o'clock. And remember, we had 30 mils. I'm going to roll the dial halfway back to 0, or to 15. Now our dial is reading true position. Now if I roll the dial back to 12 o'clock, do you think it'll still read 0? Well, let's see. No, it reads 15 mils. Since I set the value to 15 mils at a 6 o'clock position, it also reads the true position at the 12 o'clock position. 15 mils at the bottom, 15 mils at the top. The really cool thing is that regardless of where I have the shafts rotated now, I'm always reading true position. So now if I rotate the dial to 3 o'clock, what do you think the indicator will read? Well, let's see. $10 mils, which is half of the TIR value that we got from before. Wherever we have the shafts rotated now, we're always reading true position. So what happens if I roll it to 9 o'clock? You're right. Since we're reading true position, it still reads 10 mils. So as I've just demonstrated, you can zero the indicators at any position, roll it 180 degrees, half the value, and you will then be reading true position. Regardless of the orientation of the indicators, you'll be reading true position in that direction. So can you see how true position sensing can apply to your world? Even if you have an obstruction at 6 o'clock and you can't obtain a reading down there, you can still start at 3 or 9 and obtain true position values. In our next video, I'll show you how to take advantage of true position sensing. That means less measuring and less loosening and tightening of the bolts. It makes the process much more efficient. I'm Patrick from Fiberline. Thank you for watching this video, and please check out our other videos as we're out to realign America.
The dial indicator is a useful tool that can be used to measure runout, piston position, bent shafts, valves, or for brake rotor warpage. It is a simple and easy to use precision measuring tool that all mechanics must master. Some dial indicators can measure smaller than 1/1000th of an inch. Most mechanics will not require this kind of accuracy, so this lesson will focus on how to use a dial indicator that can read to within 1/1000th of an inch. The basic parts of a dial indicator are bezel, used to rotate the zero to align with the needle; markers, used to provide reference points and rarely used by the mechanic; point, contacts the surface that needs measuring and can be replaced with different types; plunger, transfers the up and down movement to the inside of the dial indicator; turn counter, counts how many times the needle does one complete revolution; pointer, points to the measured number. There are two scales on the dial indicator. The outer scale is marked in 1/1000th of an inch increments, and each 10th number is marked to make reading easier. The small inner scale is numbered 1 through 9, and each number represents 100,000ths of an inch. For each complete revolution of the outer scale, the small inner scale moves one number up or down. Before using the indicator, it must be mounted so there is no movement between the dial indicator and the part to be measured. If there is any looseness or movement, the reading will not be accurate. Position the indicator 90 degrees to the face of the part being measured. Press the dial indicator against the part so that the plunger is depressed about half of its travel. This loading of the plunger ensures the indicator can function properly. Lock the indicator into place and carefully rotate the part while you observe the dial readings. Read the dial face straight on so as not to read the wrong measurement. If the pointer does not move while the part is being rotated, the part has no runout or surface distortion. If it moves, there is runout or surface distortion. Stop when the needle moves to the maximum position to the left and rotate the bezel so the zero aligns with the pointer. Continue rotating the part until the pointer gets to the maximum position on the right. The total movement between the left and right measurements is how much runout or distortion the part has. In this example, the needle starts at 0 and moves 6/1000ths to the right. The total runout of this part is 6/1000ths of an inch. In this example, the needle starts at 0 and moves between the 1/1000ths and 2/1000ths inch lines. Since each line is 1/1000th of an inch, if the needle is between them, it can be either rounded up or counted as 5/10,000ths of an inch. The total runout for this part is 15/10,000ths of an inch.